So, in the last lecture I had derived for you the Peclet number relationship for the Nusselt number or the Sherwood number for the flow around a spherical particle. Okay. We had considered a particle on whose surface the concentration was C naught, the concentration far from the surface was C infinity. We had a flow past the particle with free stream velocity upstream of the particle to be capital U, and we had prescribed velocities on the radial and the azimuthal direction. This was symmetric in the meridional direction, and therefore, we had written down this as the mass conservation equation with prescribed velocities in the radial and the azimuthal direction. Now, u r and u theta we had expanded in a thin region near the surface of the particle, anticipating that when the Peclet number is large, the disturbance to the concentration due to diffusion from the particle will be restricted to the thin region near the surface. Okay. In terms of this, the u theta, the streamwise velocity, was proportional to distance from the surface as expected from the no slip condition. The velocity perpendicular to the surface was quadratic in the distance from the surface. Okay. These were inserted into the conservation equations, and we had used a similarity variable as the distance from the surface. All of these distances are scaled by capital R. Okay. So, the distance from the surface scaled by capital R divided by a boundary layer thickness, which is a function of the downstream distance theta. Okay. So, that is where we had started, and then we had written down equations in terms of the similarity variable and solved and simplified that in terms of the similarity variable. Now, we had got two equations. One is a condition on the boundary layer thickness delta, a condition on the boundary layer thickness delta, which has to be equal to a constant if this equation is only a function of the similarity variable eta. So, that was one condition. This has to be a constant if the equation in the limit of high Peclet number depends only upon the dimensionless distance from the surface and not on the Peclet number. So, this is the condition for that. The second was the equation for the concentration field in terms of the similarity variable eta. This is identical to what we got for the flow past a flat plate. It will also be identical for any other configuration with a no slip condition at the surface. And for that reason, the solution for this is also identical to what we had got for a flat plate. It will be identical for any other configuration that we use. The second solution equation was the equation for the boundary layer thickness. We found that this equation has to be satisfied in order for the equation to be the concentration equation to depend only upon eta and not individually on Peclet number and the boundary layer thickness. This we had solved. This is an inhomogeneous equation. You can solve it to get a solution for delta. This solution is finite at the upstream stagnation point in front of the sphere. The upstream side it is finite because the flow is incident on the sphere. Therefore, the boundary layer thickness has to be finite at this point because the flow is inward and there is diffusion outward from the sphere, and because of that at this upstream stagnation point you have diffusion coming outward from the sphere, and the fluid velocity itself is inward and goes around. At that point the boundary layer thickness has to be finite. With that condition we had fixed the constant in this equation. This implies that at the downstream section the solution automatically tells you that the boundary layer thickness has to go to infinity at the downstream section. The reason is because diffusion is outwards and convection is also happening downstream, and because of that the boundary layer thickness goes to infinity in this wake region at the rear of this sphere. In order to solve for that, we have to consider a thin angle at the downstream side where the wake is located and solve for that. Turns out that is not necessary for solving our problem, because when the boundary layer thickness goes to infinity, the flux which goes as the inverse of the boundary layer thickness goes to 0. Therefore, the flux itself is well defined even though when the boundary layer thickness goes to infinity. Okay. So, the equation that for the flux that we had depended upon this boundary layer thickness. That boundary layer thickness once again went as Peclet number to the minus 1/3 times some function of angle. That means that the flux has to go as Peclet number to the plus 1/3 times some function of angle. Okay. Peclet number to the plus 1/3 times some function of angle. To find the average flux, I just integrate over the entire angle and divide by 4 pi r square, the surface area. Okay. This integral can be done. Okay. I will not go into the details of how it is done, but it can be done. And if you do it, you get this expression, Peclet number to the 1/3 times some constant. For any flow past any solid surface with a no slip boundary condition at the surface, the equation will always be Peclet number to the 1/3 power. Okay. And that is because the boundary layer thickness goes as P to the minus 1/3 in such a way that convection and diffusion are of equal magnitude near the surface. Convective term is proportional to the Peclet number times the velocity close to the surface. That velocity is increasing linearly, therefore, it is proportional to delta. Diffusive term goes as 1 over delta square. It has two derivatives with respect to cross stream direction. So, if Peclet number times delta is comparable to 1 over delta square, boundary layer thickness has to be Peclet number to the minus 1/3. Therefore, the flux, the Nusselt number, or in this case, since it is mass transfer, it should be the Sherwood number. Okay. It will always go as Peclet number to the plus 1/3 power times some constant. That constant has to be determined by evaluating the solutions for the boundary layer thickness. So, what about situations where we do not have a no slip condition? We have already seen one such, okay, the flow of a falling film of fluid, okay, into which there is mass transport. Okay. At the surface, the concentration is the solubility, and then I have C naught far from the surface. Okay. And for in this case, this is the x coordinate, this is the y coordinate. Okay. So, I have at y is equal to 0, C is equal to the surface concentration. Okay. If I consider that the boundary layer thickness is much smaller than the fluid thickness, the thickness of the fluid film, okay, then I can say that as y goes to infinity, okay, C is equal to the undisturbed concentration. Let me call that as C infinity, okay, just to avoid confusion. Okay. And at x is equal to 0, C is equal to C infinity for all y. Okay. So, at this point is where the contact starts between the gas and the liquid. Okay. This is the point at which the contact starts between the gas and the liquid. At that point, C is equal to C infinity for all y. Okay. We define the concentration field C star is equal to C minus C infinity by Cs minus C infinity. Okay. Therefore, this is C star is equal to 1, C star equals 0, C star equals 0. And the velocity, the equation for the concentration is the form Ux partial C by partial x is equal to balance between downstream convection and cross stream diffusion. Okay. This Ux at the surface, okay, goes to a constant value. Okay. In fact, if I have this, okay, this h as the thickness of the fluid film, Ux will be equal to, okay, this constant u into 1 minus y by h the whole square. Okay. It will be a parabolic profile. We have solved for that, for the flow down an inclined plane. Okay. And this configuration is exactly identical to what we had already solved in this class, okay, where we did similarity variables. Okay. So, the Ux is equal to u, we had assumed that it was just equal to a constant velocity, okay, close to the surface. Okay. and for that we had got this solution. Okay. And you can get the exact identical solution if you say that u into 1 minus y by h the whole square, okay, to partial c by partial x is equal to d partial square c by partial y square. Okay. And then I express it in terms of a similarity variable, eta is equal to y by delta of x. Okay. Okay. Therefore, partial by partial y is equal to partial eta by partial y, partial by partial eta is equal to 1 by delta partial by partial eta, okay, and partial by partial x is equal to partial So, therefore, you can write this as u into 1 minus delta eta the whole square by h square, okay, into minus eta by delta d delta by dx. Okay. This term y by delta square can be written as eta by delta. Okay. Y by delta square can be written as eta by delta. Okay. Since delta is small compared to h and eta is of order 1, this term can be neglected, and we will get back the equation that we had earlier for this flow past a falling film. Okay. My apologies, I should have a diffusion coefficient in here. Okay. So, I will get minus u by d, okay, eta by delta okay, okay, into So, this is the equation that I would get, okay, if I express the equation in terms of the similarity variable. Now, I can separate this out into two parts, one of which depends only on the boundary layer thickness, the other which depends only upon eta. Okay. So, I will get u delta by d, okay, into minus eta partial c star by partial eta. Okay. So, that is going to be the equation with the boundary conditions. Okay. Y is equal to 0 corresponds to eta equals 0, y goes to infinity corresponds to eta equals infinity, okay, eta goes to infinity, x is equal to 0 for all y, okay, also corresponds to eta going to infinity. Okay. So, as eta goes to infinity, the similarity variable goes to infinity, c star is 0, at eta is equal to 0, c star is equal to 1. So, I have to solve this subject to those boundary conditions. Okay. So, the equation that I have is u d by, sorry, for a similarity solution to exist, you require that u delta by d, d delta by dx has to be equal to some constant. That constant without loss of generality can be set equal to 1. Okay. The solution in terms of eta will depend on the constant, but the solution in terms of y will not depend on the constant. Okay. If that is equal to 1, then the solution for the concentration field becomes partial C star by partial eta. Okay. You can integrate this once to get partial C star by partial eta is equal to some constant e power minus eta square by 2, okay, and C star is equal to C e power minus eta square by 2 plus plus some constant d, and I have boundary conditions at eta is equal to 0, C star is equal to 1, and eta tends to infinity, C star is equal to 0. I can solve this subject to these boundary conditions to get C star is equal to 1 minus we had got a solution very similar to this, okay, for the falling film earlier, except that I had redefined this as eta square by 4. Okay, that was the only difference. Okay, the factor in the definition of eta. Okay. So, this is the solution for the concentration field. Okay. Now, I have to solve the other part to find out what is the boundary layer thickness. Okay. This part d delta square by dx, okay, into half. Okay. Half d delta square by dx is delta d delta by dx, okay, just differentiating by chain rule, okay, is equal to d by u, okay, which means that delta square is equal to 2 dx by u plus a constant, okay, where d is the diffusion coefficient, okay, where d is the diffusion coefficient. Okay. Therefore, how do we determine the constant? We know that at the entrance to the test section, okay, at the entrance to the test section at x is equal to 0, no diffusion has taken place yet, okay, as the film is falling down. At the entrance to the test section, there has not yet been any diffusion taking place. What that means is that at x is equal to 0, the boundary layer thickness has to be equal to 0. Which means that at x is equal to 0, delta is equal to 0, okay, which implies that this constant is equal to 0 in this equation. Okay. Therefore, I get the boundary layer thickness as d is equal to root of 2 dx by u. Okay. So, that is the equation for the boundary layer thickness, okay, and this is the equation for the concentration field. Now, from this I can find out what is the mass flux. Okay. Mass flux is equal to d, okay, partial c by partial y at the entrance to the film y is equal to 0. Okay. It will be equal to d into Cs minus C infinity by delta partial c by partial eta, eta is equal to 0. I should have a negative sign here because the flux is in the direction of decreasing concentration. So, is equal to minus d, okay, Cs minus C infinity by delta into partial c by partial eta, okay, is just equal to this constant. Okay, the partial c by partial eta is just equal to this constant, okay, which turned out to be root of 2 by pi for the boundary conditions to be satisfied. Okay. So, I get minus root of 2 by pi. Okay. So, this is equal to d into Cs minus C infinity by, okay, okay, into root of 2 by pi. Okay. So, that is the local flux at each location x. Okay. The boundary layer thickness increases as x to the half in this case. Okay. If you recall, for the flow past a flat plate, the boundary layer thickness increased as x to the 1/3. In this case, it increases as x to the half, which means that the flux decreases x to the minus half. It decreases as 1 over square root of the downstream distance. Now we can calculate the average flux. Okay. The average flux over a length L, okay, is going to be equal to 1 over L integral 0 to L dx times the local flux at the location x. So, this will be equal to d into Cs minus C infinity divided by, okay, root of 2d by u, okay, root of 2 by pi integral 0 to L dx times x to the minus half. Okay. These two will actually cancel out, these square roots of 2 will cancel out, okay, and I will get d into Cs minus C infinity by root d by u into root pi. Okay. Integral of x to the minus half is 2 into x to the plus half. Okay. So, I will get 1 over L into 2 into x to the half between 0 and L. Okay. So, this is going to be equal to d into Cs minus C infinity by root pi d by u, okay, into 2 divided by L to the half. So, that is the equation for the average flux. Now, the Sherwood number, okay, is going to be equal to the average flux by, okay, d delta C by L. Okay. Okay. The Sherwood number is the average flux divided by d delta C by L. Okay. Okay. My apologies. Okay. So, I should have a factor of 2 here, that is how it is defined usually. Okay. So, this is going to be equal to d into Cs minus C infinity, okay, into 2 divided by root of d L by u, okay, and in the denominator I have root pi, okay, root pi coming out of this, and then I will have a 2 times j, okay, 2 times the flux divided by d into Cs minus C infinity by L. Okay. So, this ends up being 4 by root pi, okay, into, if you work out everything, you will get root of u L by d. Okay. And this is approximately 2.25 times the Peclet number based upon L to the half power. Okay. So, that is the solution for the flow past in a falling film. If you recall, when we did the similarity solutions earlier, we had got this exact same solution. We had done it by drawing an analogy between the film falling the streamwise distance x with the time elapsed since you had imposed a concentration field at the base when we discussed similarity solutions at the beginning of the course. This is the more formal way to do it, and the procedure is simple. You express everything in terms of a boundary layer thickness and then express the velocity field in terms of the boundary layer thickness very close to the surface. Once that is done, you have to have an equation which contains, okay, the equation that you get will contain, okay, 2 conditions. Okay. One will be a condition, okay, under which this equation is a similarity equation. Okay. That is the condition under which the equation that we have here is a similarity equation. Okay. The equation is a similarity equation only if the term in this red box is 1, is a constant, can be any constant value. Okay. The final result will not depend upon that. The second is the similarity equation as well. Okay. For the flow past a solid surface, whether it was a flat surface or a spherical particle, I showed you that this second part turns out to be identical. Okay. What changes is the equation for the boundary layer thickness. Okay. That is the only thing that changes. The condition, the equation in terms of the similarity variable turns out to be exactly the same. Okay. The same applies in this case as well. The equation that I get in terms of the similarity variable will turn out to be the same regardless if you have a flat surface, a spherical surface or some other shaped surface. The only thing that changes is the equation, the similarity condition on the boundary layer thickness for the equation to have a similarity solution. That is the only thing that changes. We can use that condition in order to solve for this similarity equation for the boundary layer thickness. This solution is common. Okay. For all problems, this solution is common. I will show you that in the next lecture by taking the example of a spherical bubble rather than a flat surface. Okay. I will do this exact same procedure for a spherical bubble in terms of instead of a flat surface. So, let me briefly give you how the equation for the bubble looks. Okay. It is a configuration similar to what we had in the previous class, okay, for a solid surface. Okay. You have a spherical bubble with a velocity u incident on it. Okay. That the fluid velocity field goes around this bubble. Okay. If we choose the same spherical coordinate system with r and azimuthal angle theta from the upstream directed axis, okay, from the upstream directed axis, the angle theta from the upstream directed axis. In this spherical coordinate system, the equation of the concentration field is going to be equal to u r partial c by partial r plus Now, we have enough experience with boundary layers to know that we can neglect the streamwise diffusion in comparison to the cross stream diffusion. Okay. So, that the equation becomes a balance between streamwise convection and cross stream diffusion. Boundary conditions at the surface, C is equal to C naught at the surface, C is equal to C infinity far away. Okay. So, we can define C star is equal to C minus C infinity by. We need to know what these velocities are for the laminar flow. Okay. We need to know what these velocities are for the laminar flow. In this particular case, for the laminar flow, the velocities will be of the form u r is equal to minus u into 1 minus cos theta So, these are the velocities for a laminar flow, for the flow past a bubble. Okay. If I define the scale velocities, u r star is equal to u r by u and the scale radius, okay, then I will get and now in the if I substitute these into the equations, okay, okay, what I will get is the Peclet number u into r divided by d into and now I have to look at a thin boundary layer near the surface. Okay, of thickness delta, which is a function of theta. Okay. So, the distance from the surface, okay, r star minus 1 is the scaled distance from the surface, the distance from the surface scaled by the radius of the sphere. This I can write it as a similarity variable times delta of theta. Okay. Exactly the same procedure that we had used earlier. Okay. Therefore, in this equation I will write r star is equal to 1 plus eta delta of theta, okay, where delta is a small number. Okay. Delta is the boundary layer thickness, which is a small number. So, on the left side I will get the Peclet number. Okay. I am sorry, before I do that I have to expand out the velocities in terms of delta. Okay. So, I know that u r star is equal to 1 minus 1 by r star. If I expand this out in a series in delta, I will get 1 minus delta eta. So, this will turn out to be equal to minus of 1 minus which this 1's will cancel out, okay, and this will just turn out to be equal to, okay, minus of delta eta into cos theta. Okay. Now, the second term u theta is equal to 1 minus 1 by 2 into 1 plus delta y, okay, into sin theta. Okay. This just turns out to be equal to, this term here goes to a half as delta goes to 0. Okay. So, this term here just turns out to be half sin theta. Okay. So, these are the expressions for u r and u theta close to the surface. Okay. Note that u theta is finite now along the surface. Okay. U theta is non-zero along the surface. That is because we have a surface of a bubble where the velocity can be non-zero at the surface. Okay. So, u theta is actually non-zero at the surface, and u r, okay, is proportional to the distance from the surface. At the surface itself there is a no penetration condition. So, therefore, you cannot have any velocity that is perpendicular to the surface at the surface, because there is no penetration of the liquid into the gas. Okay. The bubble is integral. There is no penetration condition. So, therefore, the normal velocity can scale only as the distance from the surface or a higher power of the distance from the surface. Okay. The tangential velocity is finite, it is non-zero at the surface. Okay. So, this is the difference, the tangential velocity is non-zero and the normal velocity scales as the distance from the surface. This is the difference between a particle and a bubble, and we will continue this and we will see what implications it has for the mass transfer from the surface. So, I will continue this lecture in the next class and derive for you the expression for the mass transfer from a spherical bubble and discuss some of the common features of the two cases, where you have a no slip condition at the surface and where you have a slip condition at the surface. Why do you get one type of scaling in the case of no slip condition as Peclet number to the 1/3 power, another type of scaling with slip condition as Peclet number to the half power. So, we will continue this in the next lecture. I will see you then.